and an interstellar object called 3I Atlas is forcing scientists to slow down and reconsider what they thought they understood. This object is accelerating without clear gravitational cause, surrounded by an unusually large hydrogen cloud and emitting a diffuse X-ray halo that does not fit existing models. Then came the unexpected moment. The MAVEN spacecraft briefly detected these signals and went completely silent. Chemical data confirm water, methanol, and hydrogen cyanide, yet the object remains dim, optically strange, and marked by a rare double tail. As its closest approach nears, 3I Atlas remains unresolved. If you value careful science over speculation, like the video and subscribe to the channel. Now, let's begin. On December 15th, NASA released a working hypothesis addressing the behavior of the interstellar object known as 3I Atlas. According to this assessment, the object is traveling at an unusually high velocity and shows signs of non-gravitational acceleration. This acceleration appears to align in time with the unexpected silence of the MAVEN spacecraft. Observational data suggests that 3I Atlas interacts strongly with the surrounding plasma environment, producing a rare and extended X-ray halo along with a faint electromagnetic wake that trails behind it as it moves through space. Chemical measurements add another layer of detail. Spectral analysis indicates elevated levels of methanol and hydrogen cyanide, compounds that are of interest because they are often discussed as precursors in basic chemical pathways related to life. Their presence does not imply biology, but it does support the idea that complex chemistry is not confined to planetary systems like our own. These molecules appear to be embedded within ice and released as the object responds to solar heating. A wide range of explanations has been proposed to account for the full set of observations. Some ideas focus on hydrogen-driven activity, while others consider automated surveying behavior or short-duration signal emissions. There are also models that explore subtle changes in motion linked to gravitational interactions near Jupiter. Despite these discussions, multiple lines of evidence continue to support a simpler conclusion. The detection of natural hydroxyl compounds, along with a clearly observed dual tail structure made of gas and dust, aligns with established behavior seen in icy bodies. These features indicate that 3I Atlas remains a natural object governed by physical laws that apply throughout the universe. The universe contains many forms of matter and many patterns of behavior that extend beyond what current models can fully describe. This does not mean those models are wrong, but rather that they are incomplete. In cases like this, scientific progress depends on patience, careful observation, and a willingness to accept uncertainty. Not every question receives an immediate answer, and not every anomaly points to something extraordinary. For this reason, research into 3I Atlas remains open-ended, guided by evidence rather than conclusions. As this investigation continues, time becomes an important factor. 3 days remain as the calendar moves toward December 16th, and 3I Atlas continues its quiet passage through the inner solar system. Official briefings emphasize that the object poses no risk. The calculated distances are large. The projected trajectory remains stable, and the language used by space agencies is deliberately calm. The intent is reassurance, not alarm. Public statements describe 3I Atlas as a typical interstellar comet, a fragment formed around another star, that is briefly passing through our system before returning to interstellar space. Its closest approach to Earth is projected at roughly 270 million kilometers. In astronomical terms, this distance is considered safe and routine, far beyond any region of concern. Yet beneath this steady presentation, there is a sense that the picture is not fully settled. The official narrative stresses confidence, but the data itself carries hints of hesitation. Tracking tables appear clean, yet small gaps remain. Brightness models suggest one outcome, while actual observations show another. Scientists describe 3I Atlas as behaving like a normal comet, even as its measured properties resist simple classification. Independent astronomers, including those using advanced amateur equipment, report that some expected visual signatures are missing or weaker than predicted. This discrepancy does not generate fear. Instead, it creates a quiet tension, the kind that emerges when explanations arrive faster than understanding. 5 days may be insignificant on cosmic timescales, but for 3I Atlas, 5 days represents a critical window where observation becomes opportunity. Across the globe, telescopes align with predicted coordinates. Optical instruments remain fixed on a faint point of light. Radio arrays listen for subtle signals. Data streams into archives where it will be examined and re-examined for years to come. The prevailing message remains unchanged. There is nothing unusual to see. The object is simply passing through, indifferent to our presence. History suggests that science rarely advances during periods of complete comfort. Progress often comes when observations do not fully match expectation. 3I Atlas already shows signs of such resistance. There are no alarms, no urgent bulletins, and no disruption to daily life. Yet beneath this calm surface, the object invites a deeper form of attention, not driven by fear, but by awareness. When an object older than the Sun itself enters the inner solar system, even ordinary explanations deserve careful examination. As telescopes continue to follow its projected path, 3I Atlas appears significantly dimmer than early models predicted. This is notable because it is now approaching regions where sunlight should be sufficient to trigger visible activity. Under normal conditions, solar heating causes volatile ice to sublimate. Gas expands outward, dust grains scatter light, and brightness increases in a predictable way. This pattern has been documented across decades of comet observations. With 3I Atlas, that familiar rhythm feels incomplete. Instead of a steady brightening, observers record a muted presence that barely separates itself from the background stars. Measurements place the object at roughly magnitude 11 or 12, indicating faintness that challenges assumptions about an active interstellar comet. If gas and dust are being released, the subdued visibility raises questions about how light interacts with the object's surface and surrounding material. One explanation suggests that 3I Atlas may be smaller than initially estimated, limiting the amount of reflected light. While size plays a role, it does not fully account for emissions that appear inconsistent with inferred activity levels. Another possibility focuses on surface properties. An unusually low albedo would cause the object to absorb much of the incoming light rather than reflect it, allowing it to slip quietly through observational thresholds. Some researchers consider a more subtle interpretation, They suggest that 3I Atlas may not simply reflect or absorb light, but modulate how and when it becomes visible. In this view, faintness is not a failure of detection, but a condition of observation. The object reveals enough to remain detectable, while withholding clarity. This behavior does not violate known physics, but it stretches familiar models into shapes where multiple explanations coexist without immediate resolution. Reports from independent observers reinforce this picture. Across different locations and instruments, 3I Atlas appears ghost-like, present but restrained, as though lingering at the edge of perception. The paradox deepens because the faintness is not constant. At times, the object brightens slightly, only to fade again. This variability resists simple explanation and encourages patience rather than urgency. As the countdown continues, 3I Atlas remains dim but persistent. This faintness does not suggest danger, it suggests complexity. In astronomy, the most subtle objects often carry the richest information, precisely because they demand sustained and careful attention. The story takes on added weight when attention shifts away from telescopes and toward a spacecraft already positioned deep in space. That spacecraft is MAVEN, the Mars Atmosphere and Volatile Evolution mission, which has orbited Mars reliably since the year 2014. For more than a decade, MAVEN has operated with consistency, studying the upper atmosphere of Mars and transmitting data without major interruption. In early October, MAVEN directed its instruments toward 3I Atlas as the interstellar visitor passed within tens of millions of kilometers of Mars. The observation itself was routine. The result was not. MAVEN detected an extended cloud of hydrogen surrounding the object. A structure of that scale is unexpected around such a faint body at that distance. The data were transmitted successfully. Telemetry confirmed that MAVEN was operating normally, with all systems stable. Then, on December 6th, communication ceased. The silence was complete. Spacecraft do fail, and space is unforgiving. In many cases, this explanation is sufficient, yet timing matters. MAVEN functioned normally before the observation, captured data related to 3I Atlas, and then fell silent shortly afterward. Engineers searched for signals. The Deep Space Network listened. MAVEN did not respond. Taken alone, silence proves nothing. Placed alongside other irregularities associated with 3I Atlas, the silence invites careful questions. The loss of communication does not confirm interference, intention, or cause. It simply becomes part of a broader pattern. Pattern recognition does not claim certainty. It notes alignment and asks whether multiple observations belong to the same process. From this point, scientific interpretation begins to diverge. Some researchers point to coincidence, reminding the scientific community that correlation does not imply causation. This caution is foundational in science. Others argue that repeated alignment deserves continued attention. Both positions are allowed to stand, not as competing beliefs, but as parallel working frameworks. Progress depends on letting these interpretations coexist until evidence gradually narrows the range of explanation. What remains firmly established is this: 3I Atlas passed Mars, left behind an unusual hydrogen signature and continued its inward trajectory. MAVEN, after recording that passage, ceased all communication. The absence of communication becomes part of the dataset. In astrophysics, missing information is not dismissed. Silence can carry meaning, especially when it follows a defined sequence of events. This moment does not call for fear or urgency. It calls for restraint. When a long, trusted instrument falls silent, scientists pause. They revisit assumptions, review engineering limits, examine environmental conditions, and acknowledge uncertainty as an active component of understanding. As 3I Atlas continues its approach, the silence of MAVEN remains in the background. It is not evidence of threat. It is a reminder that observation is never passive. Sometimes the universe does not respond with signals or images, but with quiet. In that quiet, 3I Atlas moves onward, carrying questions that cannot yet be resolved, only held while calculations refine its path. One of those questions involves motion itself. 3I Atlas shows a subtle but persistent deviation from purely gravitational movement. Its trajectory cannot be explained entirely by the pull of the Sun and the known mass distribution of the solar system. Astronomers describe this behavior as non-gravitational acceleration. In familiar comets, this effect is usually caused by jets of gas escaping from the surface. When ice warms and vaporizes, the escaping material produces thrust, similar to a natural propulsion system. This process almost always leaves behind a clear visual signature. Gas expands, dust spreads outward, and a bright tail forms that traces the comet's motion. With 3I Atlas, that expected signature is incomplete. The object accelerates, yet the tail that should accompany such motion appears faint, broken, and inconsistent. This mismatch creates quiet tension between theory and observation. Physics provides possible explanations, but none resolve all constraints at once. One explanation suggests that 3I Atlas may be venting material in a form that is difficult to detect. If the exhaust consists mainly of hydrogen, the lightest element, acceleration could occur without producing a dense or reflective tail. Hydrogen disperses rapidly and reflects very little light when spread across large volumes of space. Other researchers explore a broader framing. They ask whether the acceleration itself should be treated as a feature rather than a side effect. This perspective does not assert machinery or design. It simply questions whether natural processes alone account for the full behavior observed. Avi Loeb has argued that anomalies deserve careful examination rather than immediate dismissal as error. From this viewpoint, 3I Atlas becomes a test of intellectual caution. If its behavior is natural, then current models may need expansion. If the behavior resists those models, science must accept the limits of certainty. In either case, the motion of 3I Atlas carries meaning, not as evidence of technology, but as a prompt to reassess how well existing frameworks describe objects arriving from beyond our stellar neighborhood. One hypothesis frames 3I Atlas as a passive traveler with an active role. In this view, the object does not arrive to interact directly, but to observe. Automated survey concepts already exist within human engineering. Probes are designed to pass through environments, collect data and depart without interaction or communication. Applied carefully, this logic raises questions about 3I Atlas, the timing of its closest approach, its non-gravitational acceleration, and its limited visibility could align with survey-like behavior. Such a system would not require signals or responses. It could sample magnetic fields, solar wind conditions, and atmospheric boundaries simply by moving through space. This idea remains speculative. No direct evidence shows that 3I Atlas performs measurement or analysis. Still, automation offers a neutral explanation that avoids intention. In this framing, 3I Atlas is neither messenger nor threat, but a system following processes established long ago. If the hypothesis lacks support, it will fade quietly. If it holds relevance, it suggests a form of observation that notices without announcing itself. As 3I Atlas moves deeper into the inner solar system, its speed becomes a focus of precise measurement. Trajectory calculations indicate that the object accelerates from approximately 221,000 kilometers per hour to nearly 246,000 kilometers per hour near perihelion. Gravitational forces explain most of this increase, but a small residual acceleration remains. In typical comets, this excess acceleration corresponds directly to visible outgassing. Solar heating releases volatile materials that produce jets, dust clouds, and bright tails. With 3I Atlas, the acceleration is present, but the visual evidence remains subdued. Cause and effect appears slightly misaligned, creating a puzzle rather than a contradiction. One explanation again centers on composition. If 3I Atlas releases mainly hydrogen, thrust could occur with minimal optical signal. Hydrogen is difficult to detect visually, especially when spread thinly across space. Another explanation involves geometry. Jets emerging from specific orientations could produce acceleration while remaining poorly aligned with Earth-based viewing angles. These interpretations rely only on known physics applied to unfamiliar conditions. They do not require new forces, only new configurations. Yet the idea of hidden exhaust introduces a subtle shift in expectation. Acceleration does not need spectacle. Motion can exist without display. 3I Atlas appears to move with restraint. It leaves enough evidence to suggest activity, but not enough to reveal its mechanism clearly. This challenges patterns shaped by decades of comet observation, where acceleration is usually loud and obvious. Here, acceleration is quiet, allowing data to accumulate slowly rather than dramatically. Among the more conservative explanations, one considers 3I Atlas as an object interacting efficiently with its environment. This idea does not require intention, only exposure. Hydrogen is the most abundant element in the universe. It fills interstellar space, flows within the solar wind, and lingers around planets. The extended hydrogen cloud observed earlier raises the possibility that 3I Atlas may not only release material, but also interact with surrounding hydrogen-rich regions. From a physical standpoint, such interaction does not require complexity. Charged particles can be captured or redirected through magnetic processes without producing bright optical signatures. If hydrogen plays a role, Acceleration could occur while visible exhaust remains minimal. Momentum transfer through plasma interaction can be quiet, gradual, and effective over long timescales. Even weak forces accumulate measurable effects. No instrument has confirmed hydrogen collection directly, and the hypothesis remains unproven. Still, it offers a calm bridge between observation and explanation. 3I Atlas does not require engines, nor intention. Instead, it becomes an object shaped by prolonged exposure to cosmic environments. Motion arises from interaction rather than control. Energy and momentum emerge through contact with space itself. In this framing, the universe becomes part of the mechanism. 3I Atlas continues forward, guided not by visible thrust, but by subtle exchanges that leave only faint traces behind. Those same subtleties shape how the object is observed. As observational campaigns continue, the data record surrounding 3I Atlas begins to show moments of absence rather than clarity. These gaps are not dramatic. They do not arrive as sudden losses or obvious failures. Instead, they appear quietly in places where continuity is normally expected. Orbital updates arrive, then pause, then resume. Parameters adjust, stabilize, and briefly vanish from refinement. For short intervals, 3I Atlas seems to move between measurements rather than through them. In most astronomical studies, missing data reflects familiar limitations. Weather disrupts optical tracking. Solar interference overwhelms sensors. Scheduling constraints reduce coverage. These explanations account for many interruptions. With 3I Atlas, however, the pattern feels different. The object remains a high-priority target, yet its observational trail occasionally thins, even when conditions appear favorable. Some researchers attribute this to geometry. As 3I Atlas moves against dense star fields or approaches regions affected by the sun's glare, detection becomes difficult. Contrast drops, background noise increases. Separating a faint object from its surroundings requires ideal alignment that does not always occur. Others focus on surface properties. If 3I Atlas absorbs light efficiently, systems that depend on reflected photons may struggle to maintain precise tracking. The silence does not suggest disappearance. It suggests reduced visibility. 3I Atlas occupies space without clearly announcing its position. Radar systems offer limited assistance at such distances. Radio telescopes listen, but 3I Atlas emits no intentional signal. The absence of emission reinforces uncertainty. Tracking depends entirely on passive detection, and the object offers little help to those observing it. This creates an unusual dynamic. Scientists follow predictions rather than confirmations. They trust models more than direct observation. For most celestial bodies, observation corrects prediction. With 3I Atlas, prediction occasionally substitutes for observation. This reliance does not invalidate the data, but it introduces caution. Even when calculations appear stable, errors remain possible. The silence within the data does not imply concealment. It does not imply design, yet it remains part of the record. In astronomy, absence does not equal emptiness. Absence becomes a condition that shapes interpretation. as 3i Atlas continues inward. Tracking resumes and pauses in alternating rhythm, the object remains present but never fully captured, reminding observers that not all motion offers itself completely to measurement. As the calendar approaches December 19th, attention shifts from a fixed location in space to a narrow window in time. For 3i Atlas, this date represents the moment of closest observational opportunity, when distance, geometry, and instrumentation briefly align. It is a period when small changes become easier to detect and subtle behavior carries greater weight. Some researchers explore the possibility that 3i Atlas operates in intermittent modes rather than continuously PO. In engineering, systems designed for long-duration travel often conserve energy. They remain quiet for extended periods, activating only when thresholds are reached. Applied cautiously, this idea suggests a pulse scenario. 3i Atlas could remain largely inactive, then briefly intensify activity near its point of closest approach. Such a pulse would not resemble communication. It would not involve signals meant to be received. Instead, activity could take the form of concentrated internal processes, brief interactions with surrounding plasma, or short-lived changes in physical state. In this framing, silence becomes preparation rather than absence. The object conserves energy while traveling, then engages briefly when conditions offer the highest informational return. This scenario does not assume intent directed at Earth or at any observer. 3i Atlas becomes an object responding to environmental thresholds defined long before its arrival. Astrophysics already recognizes intermittent behavior in natural systems. Pulsars release energy in regular bursts. Solar flares occur suddenly after long periods of calm. Magnetospheric events build quietly, then discharge. If 3i Atlas follows a similar pattern, detection becomes difficult. A short-lived event could pass unnoticed unless instruments are aimed precisely at the right moment. This possibility introduces uncertainty, not drama. Observers may record quiet skies while assuming nothing occurred, even as the object briefly altered its state. Some suggest that a pulse might appear only indirectly. Minor disturbances in the solar wind, localized electromagnetic fluctuations, or transient anomalies could accompany such activity. None of these effects would announce themselves clearly. Subtlety remains consistent with prior observations of 3i Atlas. The pulse scenario remains hypothetical, one idea among several held in reserve. No confirmed data indicates that December 19th will differ from any other day. Yet the idea persists because it fits a broader pattern of restraint. 3i Atlas does not rush. It does not repeat unnecessarily. It does not amplify its presence. As the date approaches, instruments remain attentive. Whether silence continues or brief activity occurs, the object maintains its role as a reminder that not all events unfold on human schedules. Discussion naturally extends from signals to vulnerability. Modern space systems rely on delicate electronics that operate within narrow tolerance ranges, especially beyond Earth's protective magnetic field. Even unintentional energetic interactions can produce subtle consequences. Radiation spikes, charged particle flows, and localized electromagnetic disturbances can interfere with instruments without leaving visible damage. Spacecraft designers already account for such risks. Solar flares, cosmic rays, and plasma storms regularly test the resilience of satellites and probes throughout the solar system. In this context, 3I Atlas does not need to emit a directed signal to influence its surroundings. A brief interaction with the solar wind or a localized change in plasma conditions could momentarily stress nearby systems. The silence of certain instruments invites careful consideration. Failures often appear ordinary when viewed alone. Patterns emerge only when timing aligns with unusual external conditions. Some researchers ask whether 3I Atlas could amplify existing environmental effects by moving through charged regions of space. The object might alter electromagnetic balance without producing a detectable broadcast. This scenario does not imply hostility. Nature itself produces disruptions that exceed engineering expectations without intention or awareness. The concern lies not in threat, but in preparedness. Human technology remains sensitive to forces that operate quietly and briefly. If 3I Atlas coincided with a moment of heightened interaction, disruptions could occur without clear attribution. Engineers might diagnose faults internally, unaware of contributing external influences. Such possibilities encourage humility rather than fear. Complex systems rarely fail from single causes. They fail through combinations. As 3I Atlas continues its passage, monitoring extends beyond optics and trajectories. Electromagnetic environments, instrument health, and subtle anomalies become part of the same observational fabric, whether disruption occurs or not. 3I Atlas reinforces an enduring truth of space science. Interaction does not require communication, and influence does not require intention. That influence is often quiet, registered not as events, but as traces. As 3I Atlas advances through the solar environment, attention begins to shift from what lies ahead to what remains behind. Space is not empty. It is filled with plasma, charged particles, and magnetic fields that respond subtly to motion. When an object passes through this medium, it can leave faint traces that persist briefly before dissolving back into equilibrium. Solar observatories have reported minor irregularities in the solar wind during periods that align closely with the projected path of 3I Atlas. These irregularities do not appear as strong disturbances or sharp disruptions. Instead, they manifest as small-scale turbulence, easily overlooked unless examined through careful correlation of timing and location. From a physical standpoint, an electromagnetic wake can form whenever charged particles interact with magnetic fields. If 3I Atlas carries even a weak magnetic influence, interaction with solar plasma becomes unavoidable. This does not require intention or complexity. The object simply moves through a dynamic environment, and the environment responds. Turbulence in plasma appears as fluctuations in particle density and energy flow. For 3I Atlas, such fluctuations could arise from several natural processes. Outgassing from the surface can ionize nearby particles. Surface charging can alter local electric fields. Passive magnetic interaction can redirect plasma flow. None of these effects announce themselves dramatically. They register as background variation unless viewed within a broader framework. The presence of a wake suggests continuity rather than interruption. 3i Atlas moves forward. Space adjusts around it, and then gradually returns to balance. This pattern mirrors many natural systems. Planetary magnetospheres create bow shocks and wakes. Solar eruptions disturb plasma temporarily. Even fast-moving asteroids generate transient effects without lasting consequence. For observers, the value lies in recognition. Small disturbances help map interaction zones and refine understanding of how 3i Atlas engages with its surroundings. As distance increases, the wake fades. What remains is not disruption, but a faint imprint confirming passage through a responsive medium. One quieter hypothesis reframes this idea further. In this view, 3i Atlas is not a source of force, but a carrier of presence. Movement itself becomes a form of distribution rather than propulsion. Particles released along the object's path could persist long after its passage. Dust grains, molecules, or microscopic fragments might drift outward slowly, blending into the broader solar system. This process requires no design. Natural systems already spread material across vast distances. Comets, asteroids, and stellar winds continuously exchange matter. 3i Atlas may simply participate in that exchange. Over time, such contributions become indistinguishable from the background. Influence does not announce itself. It integrates quietly into an already complex environment. One of the most unexpected observations associated with 3i Atlas emerged not in visible light, but at high energies. Space-based instruments detected an extended halo of X-ray emission surrounding the object, stretching hundreds of thousands of kilometers into surrounding space. This feature immediately drew attention, because X-ray halos of this scale have not been documented around interstellar comets before. For 3i Atlas, the presence of X-rays added a new layer of complexity. In established cometary physics, X-ray emission arises through a process known as charge exchange. Highly charged ions carried by the solar wind collide with neutral atoms released by a comet. During these encounters, electrons transfer rapidly, and excess energy is emitted as X-ray photons. The mechanism itself is well understood. What stands out is scale. The spatial extent of the X-ray halo around 3i Atlas exceeds what models typically predict for an object with its observed level of activity. The halo extends far beyond the region where dense gas would normally concentrate. This suggests either an unusually large interaction zone or a process operating more efficiently than expected. Scientists approached these observations with caution. Instrumental artifacts, background noise, and calibration limits were carefully evaluated. Multiple datasets were compared. Even after accounting for these factors, the signal persisted. The consistency of the X-ray structure across observations strengthened confidence that the emission reflects a real physical interaction. This does not imply unfamiliar physics. One explanation suggests that 3i Atlas possesses surface or compositional properties that allow neutral material to spread thinly over a wide region. In such a configuration, charge exchange can occur across a larger volume, producing a diffuse halo rather than a compact glow. geometry may also play a role. If material surrounding 3I Atlas expands broadly rather than forming dense jets, X-ray emission would appear extended and faint rather than concentrated. In either case, the object engages energetically with its environment rather than simply reflecting sunlight. The discovery reshapes observation priorities. Optical tracking alone cannot capture the full behavior of 3I Atlas. High-energy measurements become equally important. In this quiet glow of X-ray light, the object reveals that even faint travelers can leave luminous signatures when conditions align. To understand this halo more fully, scientists focus again on charge exchange. The solar wind carries highly charged particles outward from the sun at immense speeds. When these ions encounter neutral gas released by 3I Atlas, electrons are transferred in rapid collisions. The resulting energy release appears as X-ray radiation. Charge exchange has been observed around many comets within the solar system. What distinguishes 3I Atlas is the apparent efficiency and reach of the process. If neutral atoms extend far from the nucleus, the interaction region grows accordingly. A diffuse envelope amplifies the effect without increasing brightness in visible light. Velocity also matters. The high relative speed between the solar wind and 3I Atlas increases collision rates and energy transfer. Faster encounters can produce stronger X-ray emission even when gas density remains low. In this way, motion converts directly into radiation. Scientists remain careful in interpretation. X-ray detectors are sensitive instruments, and background effects can sometimes mimic structure. Repeated observations and calibration checks help separate artifact from physical reality. So far, the emission around 3I Atlas has shown stability rather than randomness. This consistency supports a physical explanation rooted in interaction rather than isolation. 3I Atlas does not travel through empty space. It moves through a field of particles and energy. In that environment, even a quiet object can produce light without ever igniting a visible flame. As data continues to accumulate, 3I Atlas increasingly resists placement within established cometary models. Each new measurement appears to fit partially, yet never completely, into frameworks developed from objects formed within our own solar system. These models perform well for local comets, but they begin to strain when applied to an object shaped by a different stellar environment. Traditional comet models assume relatively predictable ratios between water, carbon dioxide, and other volatile compounds. For 3I Atlas, those ratios appear shifted. Observations suggest that carbon dioxide is present at levels significantly higher than expected when compared to water ice. This imbalance draws attention because it challenges long-held assumptions about how icy bodies evolve under prolonged exposure to sunlight. In the solar system, repeated passes near the sun gradually strip comets of their most volatile materials. Over time, water becomes dominant, while compounds like carbon dioxide diminish. 3I Atlas does not follow this pattern cleanly. Despite its immense age, it appears to retain volatile-rich material that should have been depleted long ago under familiar conditions. One explanation proposes that 3I Atlas developed a thick, irradiated outer crust during its interstellar journey. Over millions or even billions of years in deep space, exposure to cosmic rays and ultraviolet radiation could harden the surface This layer would act as insulation, protecting deeper reservoirs of volatile material. When heating finally occurs, gas release would be uneven and delayed, producing behavior that differs from expectations based on surface observations alone. If this model is correct, 3I Atlas is not a uniform body. It is a layered archive. What instruments detect at the surface may represent only a fraction of the complexity beneath. Surface measurements would then underestimate internal diversity, creating apparent contradictions between chemistry, brightness, and activity. Other researchers suggest a broader explanation. Interstellar objects may simply be more diverse than previously assumed. The solar system provides a narrow sample. 3I Atlas may not be unusual in its own context. It may be the first object of its class, observed closely enough to reveal variation that existing categories cannot easily absorb. From this perspective, resistance to classification becomes informative rather than problematic. Models built from local examples may be too limited to describe material formed under different conditions. The difficulty lies not in forcing 3I Atlas into known categories, but in accepting that those categories may be incomplete. As researchers adjust their models, each improvement resolves one discrepancy while exposing another. Brightness, chemistry, acceleration, and environmental interaction refuse to align simultaneously. This resistance does not weaken science. It strengthens it by revealing where understanding ends and investigation begins. For 3I Atlas, defiance is not rebellion. It is simply the consequence of arriving from elsewhere, carrying a history that existing equations were never designed to describe. While models evolve, the object itself remains unchanged. It continues its quiet passage, demonstrating that while physical laws are universal, outcomes are not always uniform. Radio observations add another layer to this evolving portrait. Using the Atacama Large Millimeter Array, astronomers detected chemical signatures that stand apart from expectations shaped by decades of comet study. Among these, methanol appears in unusually high abundance. For 3I Atlas, methanol is present at concentrations several times higher than those measured in typical solar system comets. Methanol matters because it is not merely a byproduct of simple ice chemistry. It is a foundational molecule in pathways that lead toward more complex organic compounds. The same observations identified hydrogen cyanide within the expanding coma. For 3I Atlas, hydrogen cyanide is not a trivial trace. In laboratory environments, this molecule participates in reactions that produce amino acids and nucleic acid bases. These reactions do not create life directly, but they establish chemical routes toward biological complexity. The combined presence of methanol and hydrogen cyanide at elevated levels suggests a chemically rich interior. 3I Atlas appears to carry material shaped under conditions different from those near the early sun. One explanation focuses on formation. If the object originated in a colder or more radiation-shielded region of another stellar system, volatile compounds could remain preserved over vast time spans. Another explanation shifts focus from origin to journey. Over billions of years in interstellar space, simple ices can undergo transformation. Cosmic rays, ultraviolet radiation, and extremely low temperatures drive slow chemical reactions. In this view, time itself becomes an active ingredient. 3I Atlas accumulates complexity gradually, not through sudden events, but through prolonged exposure. Scientists approach these findings with care. Chemical detections rely on spectral interpretation, and overlapping signals can introduce uncertainty. Repeated measurements help reduce ambiguity. So far, the chemical profile of 3I Atlas has remained consistent across observations. This consistency encourages reflection rather than premature conclusion. The chemistry does not imply biology, intention, or design. It points instead toward abundance. Organic building blocks may be far more widespread in the galaxy than previously assumed. For 3I Atlas, carrying such material does not make it special in purpose. It makes it informative in context. The object becomes a messenger of distant environments, not through communication, but through composition, in the quiet language of molecules. 3I Atlas suggests that the ingredients for complexity travel widely, waiting for suitable conditions to assemble further. This naturally raises a broader question about distribution rather than origin. When complex organic molecules appear in high concentration, attention shifts from how they formed to how far they may travel. The concept known as panspermia addresses this question cautiously. In this framework, objects like 3I Atlas do not transport life itself. They transport chemical ingredients that make life possible under the right conditions. Methanol and hydrogen cyanide serve as bridges rather than destinations. Laboratory experiments show that given energy and time, such compounds can evolve toward biological precursors. 3I Atlas provides neither environment nor activation. It offers delivery. This distinction matters. Panspermia does not claim that life arrives fully formed. It proposes that chemistry moves efficiently across cosmic distances. Interstellar space offers stability. Cold temperatures and isolation preserve fragile molecules over immense periods. If objects like 3I Atlas pass through many planetary systems, distribution becomes cumulative. Each encounter contributes material to environments already rich with potential. No evidence suggests that 3I Atlas seeded life anywhere. Yet chemistry does not require intention to spread. Motion alone accomplishes transport. In this view, panspermia becomes a quiet process rather than a dramatic claim. Over billions of years, objects like 3I Atlas may help ensure that complexity is never confined to a single place. As the object continues its passage, visual observations reveal a familiar structure. High-resolution imaging shows two distinct tails extending from the nucleus. One tail consists primarily of dust. It curves gently, shaped by orbital motion and pressure from sunlight. The second tail is composed of plasma. This plasma tail appears straighter and aligns closely with the direction of the solar wind. Such dual tail formation is well documented among comets native to the solar system. Observing the same structure in 3I Atlas carries important implications. Despite its interstellar origin, the object responds to solar forces in ways that mirror local bodies. Gravity, radiation pressure, and plasma interaction operate universally. Regardless of where an object formed, this universality offers a moment of stability within broader uncertainty. 3I Atlas may challenge models, but it does not escape physical law. In its twin tails, the object quietly affirms that even travelers from beyond the solar system remain subject to the same forces that shape everything moving through the sun's domain. Even as 3I Atlas challenges certain expectations, the foundation of physical law remains consistent. The presence of two distinct tails confirms ongoing interaction with sunlight and the solar wind. 3I Atlas is not inert, and it is not isolated from its surroundings. Energy flows across its surface. Material responds, and space reacts in familiar ways. At the same time, subtle differences persist. The brightness, structure, and variability of the tails do not mirror those of many well-studied comets. The dust tail appears thinner and more uneven. The plasma tail shows variations in alignment and intensity that change over short intervals. These details do not contradict cometary physics, but they remind observers that shared forces do not produce identical outcomes. Universality does not erase diversity. Gravity, radiation pressure, and plasma interaction apply everywhere. Yet their expression depends on composition, structure, and history. For 3I Atlas, the twin tails represent both familiarity and contrast. The object behaves like a comet, but not exactly like any comet previously observed in such detail. This balance encourages restraint. Neither dismissal nor exaggeration helps understanding. The dual tails do not resolve outstanding questions. They simply anchor 3I Atlas within known physics while leaving room for interpretation. In this sense, the object bridges the familiar and the unknown. Physical laws remain intact, even as the specific story of 3I Atlas continues to unfold beyond expectation. High-resolution imaging adds another layer to this picture. Detailed analysis reveals patterns suggesting internal activity rather than simple surface erosion. Astronomers identify spiral-shaped jet features that emerge intermittently from the surface. These structures cannot be explained by uniform solar heating alone. The jets resemble a process known as cryovolcanism. In cryovolcanism, volatile ices such as carbon dioxide or carbon monoxide erupt through fractures, carrying gas and fine particles into space. For 3I Atlas, this mechanism offers a coherent explanation for multiple observations at once. Localized eruptions can produce directed outflows without requiring widespread surface activity. This behavior aligns with the object's muted brightness. Instead of a broad, luminous coma, activity remains concentrated in specific regions that activate briefly and then subside. Cryovolcanism also fits the idea of an aged surface. Over billions of years, radiation exposure could have formed a hardened outer crust, trapping volatile material beneath. When solar heat penetrates this crust, pressure builds. Release occurs suddenly rather than gradually, producing narrow jets instead of a uniform glow. This process is not exotic. Cryovolcanism has been documented on icy moons and comets within the solar system. Its presence on 3I Atlas reinforces a key idea. An interstellar origin does not exempt an object from familiar physical processes. At the same time, the scale and persistence of these jets remain unusual. For 3I 3I Atlas. Cryovolcanism appears not as a rare event, but as a recurring mode of interaction with sunlight. The object is neither dormant nor fully predictable. It is shaped by internal dynamics that respond selectively to external energy. As observations continue, another feature draws attention. 3I Atlas begins to display a faint green coloration. In comets, green light is often associated with diatomic carbon, a molecule commonly referred to as C2. Under typical conditions, green emission aligns closely with spectroscopic detection of that molecule. For 3I Atlas, that alignment does not occur. Spectral analysis suggests that diatomic carbon is depleted rather than abundant. This creates a paradox in which color and chemistry no longer match expected patterns. One possibility is that an unfamiliar molecule produces the green emission. If so, 3I Atlas may contain compounds not yet fully catalogued in cometry spectra. Another explanation focuses on scattering rather than emission. Dust grains surrounding 3I Atlas may possess optical properties that favor green wavelengths when illuminated by sunlight. In this case, color emerges from interaction between light and texture, not from chemical emission. The object reflects selectively rather than glowing directly. A third interpretation considers transient processes. Short-lived reactions within the coma could briefly generate green light without leaving a stable spectral signature. None of these explanations fully resolves the paradox. Each accounts for part of the observation while leaving uncertainty intact. The green glow does not indicate danger or intent. It signals complexity. It reminds observers that visual cues can mislead when isolated from context. For 3I Atlas, the shifting green hue reinforces a broader pattern. The object behaves consistently enough to be studied, yet unpredictably enough to resist simple classification. As the color fades and returns with changing conditions, 3I Atlas continues forward. The green light remains not a message, but a question suspended quietly in motion. Radio observations provide a stabilizing reference amid this uncertainty. Using sensitive radio arrays, astronomers detect the absorption signature of hydroxyl molecules associated with 3I Atlas. Hydroxyl forms when water molecules break apart under solar radiation. For 3I Atlas, the presence of hydroxyl serves as direct evidence of water-ice sublimation. This confirmation anchors interpretation. The object is a natural icy body interacting with sunlight in ways consistent with established cometry physics. The hydroxyl signal appears at expected frequencies and intensities. No alternative explanation competes strongly with a water-based origin. This matters because it grounds speculation in reality. Even as 3I Atlas displays unusual behavior, its core composition remains familiar. Water ice implies thermal response rather than artificial control. As the object approaches the sun, solar energy naturally drives chemical transformation. Water-driven outgassing also contributes to earlier observations. It supports dust release, plasma interaction, and coma formation. By confirming water, scientists narrow the field of interpretation. Not every anomaly demands an extraordinary explanation. Instead, 3I Atlas appears to blend the ordinary with the unfamiliar. Some properties follow expectations, others resist easy categorization. This balance reinforces scientific caution. Progress comes from isolating what is known before confronting what remains uncertain. For 3I Atlas, hydroxyl marks a point of clarity amid broader complexity. As calculations extend beyond the inner solar system, attention begins to shift toward a future gravitational alignment involving 3I Atlas. Orbital projections indicate that the object will pass near Jupiter at a distance comparable to the planet's Hill radius. This proximity appears unusually precise, occupying a region where gravitational influence becomes especially efficient.